let's start with a page that has like that transverse wave on it and the dots on across the top of the page. So let's start with this idea, okay? What type of wave is depicted? A transverse wave or a longitudinal wave?
This one.
Longitudinal.
It's longitudinal. Okay? Why is it a longitudinal wave?
It's like horizontal.
Yeah, so what's happening is that those dots are particles. This is like a sound wave. Okay? So what's happening is that it's representative of, remember how sound works. This is why I had you all do the lab with tuning forks, right? So you understand, oh, tuning forks vibrate back and forth. It sends a compression, and then when it pulls back, so when that compresses that air, that creates a region of high pressure. When it pulls back, it creates a region of low pressure. So that vibrates back and forth. So what you hear is a high and low pressure sense. That's what when you hear anything, remember, your brain has no direct contact with the outside world. If it does, something's gone horribly wrong. But, so, what you hear as sound is nothing but a pressure wave that hits your eardrum vibrates, it sends that signal through the bones of the inner ear to the auditory nerve. Your auditory nerve picks that up, and then your brain says, oh, Burkamp's talking about frequency and longitudinal waves. So what you hear as my voice is nothing more than a disturbance in the air pressure in this room that makes your eardrum vibrates and your brain says, oh, he's talking about longitudinal waves. Okay?
My brain didn't like that.
Sorry. Just tell me. Okay, so
Sound waves are longitudinal.
sound waves of longitudinal, light is transverse. Light goes like this. So, what does this distance represent where it repeats itself?
Can you repeat that? No.
On the sheet, it has this distance here where you have a compression here and you have a matching compression on the other side. So what do you think that distance represents?
Wavelength.
That's going to be the wavelength. Now, this distance here, you don't really know what that means. It isn't the amplitude, because you know we can't talk about amplitude based upon that. Now, obviously, you experience different amplitudes when you hear things. So, if I talk really quietly, okay?
What?
I can hear you.
If I talk really quietly.
Okay.
Basically, what's happening is that I'm not sending out much of an energy pulse, okay? There isn't much of an amplitude to it. Now, if I talk real loud, right?
What?
Did the sound travel any faster when I talked loud?
No.
No. Why did you hear it louder?
Bigger amplitude.
Bigger amplitude, right? Now, if we stand at one end of the hall, and we stand at the other end, we just have a normal conversation, you're not going to be able to hear the other end. Why?
It spreads out.
Yeah, that pressure is so spread out, it's still there, but that pressure is so spread out that you can't hear it because your vibrations isn't enough to make your eardrum pick that up, okay? So the only difference between talking very quietly and yelling is the energy that I put into it, okay? It's that amplitude, it's how much energy reaches your eardrums. Okay, so with that said, let's talk about that question down there at the bottom. So down there, that next question down here, you've got this. So what type of wave is represented here? This is a transverse wave, okay? So, it says transverse wave is traveling on a string. The graph above shows the position as a function of time. So imagine, because you kind of got to visualize this. So imagine this is a yellow photon, okay? Yellow tennis ball. So it does two things as it travels through space. It has a forward motion like this, but it also has a vertical motion as it goes through. So you have two different movements going on. You just don't have it vibrating up and down like this. It does, but then at the same time, it's going forward. So you have two dimensions that are taking place. You have a movement from the equilibrium point, plus you have a horizontal motion as it goes through. Because if light only did this, we'd never be able to see anything. So if those light bulbs emitted photons that just did this, we'd be in darkness, okay? But conveniently, when they emit those photons, not only do they do this, they also do that, okay? Which is one of the cool things about our universe, because that's what allows us to have energy from the sun. So if the sun emitted light and the light just did this, we'd never see the sun. But conveniently, it travels out, we can see it. So with that said, okay, so look at what's going to happen. So on this one, you have this wave that's going up and down horizontally, and at the same time, it's traveling vertically, it's traveling vertically, at the same time it's traveling horizontally. So, try and answer that multiple choice question. We're going to go over it. You've got to look at the graph to figure some of this out. Let me give you a hint. Look at how far vertically that thing is going to move through one cycle. Okay? Just give you that hint. And if you're completely baffled, look at how far it travels just from here to here. Okay? Imagine this is the particle. So starting here, it goes up, back down, goes back down, goes back up. Look at the distance that will travel in one oscillation. No, shut up. So let's start with this idea. Let's just, don't worry about the problem.
Worried.
In terms of the multiple choice part of it. How far does that object travel on the way up?
0.6 meters.
0.6 meters. So as it goes through one complete oscillation, what's the total distance that it travels vertically? 2.4 meters, right? Because it goes up 0.6, down, up 0.6, down 0.6, down 0.6, up 0.6. So the total distances traveled is going to be 2.4 meters. How long did that take?
Half a second.
Half a second. Look at the graph. You start at 0. Oh, it takes a half a second to get back to that. So if you take 2.4 meters and divide that by half a second, you get, okay? So that's the vertical speed of the wave, okay? Because if you think about it, whether the fact that it's moving horizontally doesn't matter. Imagine this thing just going back and forth like this, okay? Total distance traveled, 2.4 meters. It takes a half a second. Velocity is 4.8 meters per second. Now, then we're going to double the frequency, okay? So what's the relationship between period and frequency? They're inverses of each other, right? So if you look at period equaling 1 over frequency, or frequency equaling 1 over period, right? So if this thing is going to vibrate basically twice as much in the same amount of time, okay, it's going to go back and forth, right? So what's going to happen to the period of that oscillation? Is it going to go up by a factor of 4, or is it going to be half as much? Gap, Sean. I'm going to double the frequency. I'm going to have the period, right? Because they're inverses of each other. So it's still going to travel the same 2.4 meters. So it's still going to travel the same 2.4 meters, but instead of dividing by a half a second, I'm going to divide by 0.25 seconds. So what's going to happen? What's going to be the new velocity? 9.6. Okay? So that answer is going to be 9.6. Now, let me explain the very first problem that you're going to have on the test. So, we've talked about this. Here's going to be this visual. Here's a radio antenna. Sends out a signal. Okay? And there's going to be a boat out here traveling between those. So, this is just a classic double slit experiment. Okay? So what are the variables that you can deal with? Little d. Little d, which is going to be that distance between the radio antenna. What else you got? The wavelength that's being emitted, and m, which unless I tell you differently is going to equal 1. Now, this is a navigation. This is along the coast. So if you're the boat, which one of these variables are you most worried about? L. You're worried about how far you are off from the coast. Okay, that's what you're worried about. Okay, you're trying to figure that out. Now, you're traveling along here, right? And this is what my dad did when he was in the Navy. He was a radio man. So obviously there's limitations to how far this can work. Okay, if you're out in the middle of the Pacific Ocean, this system is not going to work. You have to be within obviously a hearing signal of the radio antenna. But so what's going to happen is that just like bright lights, you're going to hit a series of maximums where you have constructive interference, and you're going to have series of destructive interference. So if you can figure out, for example, if you know what that wavelength is, and if you look at that equation, that y equals m lambda L over d. So what you can figure out is y. You can figure out, oh, how far apart am I if you know, like let's say for example, you know the boat is moving at 20 meters per second. And if you know how long it takes in between when you get your maximums, what can you figure out? So if you know that boat is traveling at 20 meters per second, and you know how long it goes in between maximums, what can you figure out? Y, you can figure out the value of y. Oh, this is how far apart these relative maximums are. So you can figure out y. You know the wavelength, because that's you have to know the wavelength of the radio signal. That's the whole point. And you're going to know how far apart those antennae are. So what's the only variable that you need to solve for if you're the navigator on the boat? L. You're trying to figure out L, which is how far you are from the coast. Now, obviously, if you get further from the coast, what's going to happen to the value of y?
It increases.
It increases. There's going to be a direct relationship there. So if you know that, if you know, oh, hey, these signals are relatively, in terms of time, close together, that means we're close to the coast. If these are a long time in between, you're a long way from the coast. Okay, so I promise you, this is going to be the first problem on the test. You mark my words.
I don't wanna
Okay.
mark them.
Well, whatever
Yeah,
you
you're
do.
gonna be busy marking
Throw
our
your lanyard
pads.
again.
I'm just telling you, this is what's going to happen.
Throw your lanyard. All right, it's been marked.
Mark.
Oh, it's just
Good
gonna
job. That's a great button.
Radio on test. Got it.
Radio test tomorrow. Probably gonna freak out. Cohen higher for class keys. No.
Yeah.
More like class clown.
I'll think about it, Kevin.
She's a clown too.
Think about it.
Yeah.
One jester.
One jester to roll them all. To roll the class of clowns.
The king of clowns.
King of clowns, bro. The king of the clowns. He's over. Literally joking. Who would be the class of clowns? I mean,
You?
class of
Cohen.
Cohen is the class of, he's the whole king of clowns.
Okay, so let me give you this.
Clash of clowns.
So you have some form of electromagnetic radiation that has a wavelength of 700 nanometers in the air. It goes into new medium glass, water, something like that, and the new wavelength becomes 500 nanometers. Okay? So I wanted to figure out a whole bunch of things. What's the new velocity, and what's the frequency in the new medium? Now, clearly, what does your answer, what does that new velocity have to be less than?
The speed of light.
It has to be less than the speed of light. Okay? So, what can you do? I want to find the index of refraction. I forgot to add that. I also want to find the index of refraction. So where could we start?
The ratio of wavelengths to find this.
So the ratio of the two wavelengths, what would that look like?
Oh, that would give you your wavelength and error over the
Just do
wavelength
C.
in the new medium.
So
Just
you're
do
going to
C
say
over-
take 700 nanometers over,
Just do C.
500 nanometers. Yeah, and that should give you your in value, right? Of the
okay? So what does your in value have to be greater than?
one.
One.
So don't do 500 over 700.
So don't
That's bad.
do 500 over 700, that would be bad.
What happens if that
This
was
light is going fast.
So somebody takes 700 divided by 500, or 7 divided by 5. What'd you get? 1.4 even?
Yeah, exactly.
0, 0,
Okay, so
0,
there's my
0,
index of
0.
refraction. So, now I've got my index of refraction, so how could I find the new velocity in the new medium? Andrew.
Divide C by that number.
So Andrew's saying, hey, I'm going to take 3.00 times 10 to the 8th meters per second, and divide that by 1.40, which has no units because it's an index. So 73 point,
2.14 times 10 to the 8th.
what'd you get?
2.14 times 10 to the 8th.
Say that again.
2.14 times 10 to the 8th meters per second.
Times 10 to the 8th meters per second. Cool.
Why can't you
I
feed
already
my
know.
ego?
Makes sense?
That leads ahead.
Less than the speed of light.
Why
Yeah.
can't you feed my ego?
Now, I want to find the frequency in the new medium. So there's a couple ways you could do this. Is your frequency going to change?
No.
So one option is that you just take the speed of light,
That's what I thought.
right? Which equals wavelength times frequency. So you know what the wavelength is, which is going to be 700 nanometers. Okay, so here's one option. Now, this is in meters per second. You got to do the conversion. What's the conversion from nanometers?
10 to the negative 6, 9.
10 to the negative 9. 9 micros.
Oh, micro is 6, you're right, you're right, you're right.
10 to the negative ninth,
I guessed, I don't have it in front of me, we're good.
okay? And that's on your blue sheet, you don't have to memorize it. Okay? So, or on the purple sheets, excuse me. So,
What'd you get?
you can find the frequency. Once you find the frequency there, you need to find it in the new medium.
No, you have it already.
No, you already have it because it's not going to change. Okay? Cool with that. All right, so let's talk about the question with the microwave. Okay? It's this 2011 Form B. So give that a try right quick.
I give up.
That's not going to end well.
Yeah, do that on the test, Cohen.
So stop that camera for a second.